guess. Now, if R is minus 20 for specific rotation. Now, what is specific rotation? It's the rotation that you observe divided by the concentration and the path length of light. Okay, so I'll give you the equation. It's on the next slide already. But if R has a specific rotation of minus 20, what is S? Plus 20. Okay, now if I make a mixture (50, 50) R and S, what should the rotation be? 0. Okay. And we call, there's a name for that mixture? Racemic, yeah. We often refer to the combination of the two as race mates. Right? The enantiomers are race mates. They're making a racemic mixture. We call them race mates. Okay, so anyways. So kind of imagine a situation. Oh, I got it. Good. I got an even number of optical isomers in this row. Anybody in this row left-handed? You're all right-handed? Okay, let's pretend the middle two, okay, are left-handed and are sinister, left-handed, and cause a negative rotation because I'm right-handed. That's my orientation to the whole world. And the other two are right-handed or positive, okay? Just pretending, okay? Not that it really is that way. And I'm a wave of light, and I'm passing through. Okay, so she's right. So which way should the light be turning? Right now it's going like this. And it runs into her. It's going to go right. So which way is that? Clockwise. Now, it's based on your orientation. So I'm passing through this way. You have to be the eyeball that's at the end over here. So what's going to happen here is, since she's right, it goes clockwise to you. It's counterclockwise to me. Right? So clockwise. And then what's going to happen? It's going to go back. Right? The same amount, but in the opposite direction. Now what's going to happen? It's going to go to the right, and now what's going to happen? It's going to go to the middle. Okay? Now that's a 50-50 mixture, right? Now let's say the first three are R, and the last one is S. Okay? So I'm coming through. R goes, and R is the positive. That's what's really important. Go positive this way, right? Then what happens? This way. And this way, and then I get to Roger, and what happens? It goes back. Okay. Well, that kind of makes sense because it's never mind. Yeah, it's the only point. I didn't make that conscious grouping in my head, but I just realized, well, I'll just make the last one different for some reason because the last one was different. But so the percentage of the mixture. Right? If you knew how far each one of these rotated the light, and you actually measured the optical rotation at the end, you could calculate the percentages of each in the mixture. That's actually what that's telling you. Because it's based on the number of each molecule that it runs across, and in a mixture that's 50-50, it's even. In a mixture that's not 50-50, it's either going to turn clockwise or counterclockwise. Okay? So, So let's say we have unequal amounts now. And this is 2-bromobutane. Okay? And the molecule on the left, let's see, this is 1, 2, 3. So this is the R molecule. And this is the S. Okay? The R, the pure enantiomer for R causes a rotational light towards the left-hand direction, right, of 23.1 degrees, so counterclockwise, so the light's going this way. The S, pure S, which is the positive rotation in this case, causes a 20.3 degree rotation to the right. the specific rotation. So that's what these numbers are, the specific rotations. You can tell kind of that they're specific rotations because of the way they've notated it here, but generally I just have to tell you this is the specific rotation. So that's for the pure substance, okay? Now, let's say you have a mixture that's 70% R and 30% S, okay? And we want to calculate what the specific rotation of the mixture is going to be. Well, 70% of it, okay, makes it go in the left-hand direction, counterclockwise direction, minus 23.1 degrees, and 30% of it makes it go to the right. Or, sorry, yeah, makes it go to the right. The S makes it go to the right, okay? So that you can actually calculate how far the light rotates simply by saying, well, 0.70 times negative 23.1. That's how much the light is going to rotate to the left. And then 0.30 times 23.1, positive, right? That's going to be how much it rotates to the right. So I'm going to whip out my handy-dandy calculator, which is actually my cell phone, which I tell people they should never use, but oh well. I don't have, there was a calculator in here the other day. Oh, here it is. All right, I lied. I have a calculator. I won't use my phone. I'm going to try to turn it on. Right, good. So I'm going to go 0.7 times 23.1 negative. That's negative 16.17. And then I'm going to do 0.3 times 23.1. And that becomes 6.93. I'll show you an easier way to do this. But you guys get the concept, right? 70% of the molecules make the light go counterclockwise, which to you is this way, and 30% make it go clockwise. Right. So the total optical rotation then is negative 9.24. So the observed rotation for this mixture is negative 9.24 degrees. Probably just say 9.2, 2 sig figs kind of thing. Okay. So this is concept. It's called the Enantiomeric Excess. You'll see why this is a handy concept in a second, but it's called the Enantiomeric Excess, or the EE. What is the enantiomeric excess for this? What do you think? What is enantiomers, right? They're the R and the S, right? The enantiomeric excess would be how much more of one there is of the other. So what do you think the E is for this? What? 0.2. No. 70 minus 30. Yeah, 0.4, yeah. You don't, I don't know, you may have divided by 2 because there's 2.
I was doing 0.7 to get it down to 50% from 0.2 difference.
Oh, yeah, okay, so we'll talk about that. So 0.7 minus 0.3, well, the enantiomeric excess, or the percent EE is what I really want right here. Percent EE is just 40. Or the fractional form is 0.4, right? So let's say you know the specific rotations, right? And you say, I want to know what the rotation of the mixture is going to be. Take the enantiomeric excess and multiply times the specific rotation. And that's all you need to do, because that's the amount above racemic that the mixture is. So think about that, okay? 70-30, right? 30% of this, well, I mean, this 30%, and 30% of this number, not 0.3, but like there's a 30 and a 40 here, right? This 30 cancels out 30% of this. Let me forget, when I say 30% of this, it sounds like I'm multiplying the two and it's making me crazy. So if I take this 30 and subtract it from 40, right? This 30 cancels 30 of this. So then I'm left with 40%. That's the enantiomeric excess. That's the part that's not racemic. Everything else is racemic and cancels out, right? So you just take, if you want to know what the observed rotation is going to be for a mixture, you're just going to say EE times the specific rotation. And that'll give you the value. And in this case, it just comes out to minus 9.24. So it's a very easy way to do the calculation. Okay. So the other way that you can think about this calculation is you can calculate the EE of a mixture simply by taking the observed rotation and dividing it by the rotation of the pure enantiomer. Because that's the fraction of rotation that's not canceled out. Make sense? Fraction of the rotation that's not canceled out. So if I have an observed specific rotation of an observed rotation of 4.6, right? What's the EE? Well, all you need to do is go 4.6, oops. In this case, divided by 23.1 times 100. I have all these notes in this bottom here that don't apply because I made another slide, basically. So let's see. 4.6 divided by 23.1. Okay. So that's 19.91. That's the percent EE. Okay. Okay, so if that's the percent EE, what are the percentages of each compound? You guys see how from like the last thing that we did, how if I take the observed rotation, divide by the specific rotation times 100, that's the percentage that's not racemic. Right? So that gives me the percent EE. But the question is, you get this number 19.9. It's not actually the percentages of each compound because those have to be 100, right? Okay. So if I want to know what's the percentage of R and S, and I have this percent EE, those aren't the same thing. How do you get the actual percentages from the percent EE? There's a real simple way to do it. Well, you don't just subtract it. Okay, let's try this. Let's call that 20, because I just hate really complicated math. I can do it, and I do enjoy it when I'm actually sitting down to do complicated math. But when it actually comes down to like in the lecture, I like to simplify as much as possible. So I try to make this one be about 20. So it's 20. Okay, let's call it 20. So percent EE is 20. So you said I could subtract it from and add it to what?
I just know that. Okay, so we have R and S.
We have R and S, right?
And you subtract those, that gives you the 20%.
But I don't have the R and S. I want to know what the R. Yeah, if I subtract those, right? Oh, it sounds so horribly complicated. Okay, let me see if I can give you a hint on how to do it. What is purely racemic? Right? And the enantiomeric excess, if the plus goes, sorry, I keep saying R and S. If the plus goes to 60, right? What does the S go to?
What, 60%?
Huh?
40%.
It'd be 40%, right? Because I have to add to be 100. But the EE for that's what? 20, right? So think about how I just did that. And then I'll show you in formula how this works. It's not too complicated. But if 50-50 is racemic and plus is 60, then minus has to be 40 because those two have to add to 100, right? Let's say the plus was 80, or not 80, let's say 70. Plus was 70. What would be 30, right? And the EE is 40. You see the pattern? It's actually really simple, okay?
So you're just like minusing the two numbers today, just the EE.
That's minusing the plus, the minus, and the plus. That gives me the EE. But the relationship between them is one's above 50 and one's below 50, right? So the simple way, this is how I usually think of these things, is